Let's get a closer look at bosons. As mentioned earlier, or in a different video, there are 4 types of boson. These are force carrier particles: the graviton, W and Z, the photon, and the gluon. These are associated with different forces. The graviton is associated with gravity, the W and Z, the weak force, the photon with electromagnetic forces, and the gluon with the strong force. Now, let's talk about the strong force first. One of the fundamental questions with regard to the nucleus is, why doesn't it fall apart? Seeing as we have so many positive charges in close proximity, why don't they repel each other and the nucleus then fall apart? Now, we tend to explain that away by saying that that's the role of the neutrons. And to a degree, that isn't a complete lie, but there's more to it. Now, we're going to analyze this situation, the why don't the protons repel each other and the nucleus fall apart. We're going to look at the forces acting. We know that there are gravitational forces keeping the 2 protons together. They have mass, so there has to be a gravitational force. But there's also an electrostatic force due to the fact that they both have charges. Now, if we were to calculate both of those forces, they should balance. Why? Because, well, the nucleus doesn't fall apart, so it must be balanced. We can calculate the gravitational force using Newton's law, and we can calculate the electrostatic force by using the Coulomb law, right? So stop the video and work out these 2 values. You would have to use the radius of the proton. Feel free to search for that value and apply it to both equations. You should get a value approximately of 57.5 newtons. That is the repulsive force acting. That's huge. The gravitational force that's acting is this one, 4.7 times 10 to the minus 35. The forces most definitely do not balance, and so the nucleus should literally explode, but it doesn't. The reason why the nucleus does not fall apart is because the gravitational force is not the only force binding the 2 particles together. At a distance equivalent to approximately 1 nucleon separation, what you have is an incredibly strong attractive force. This attractive force for much smaller distances becomes very repulsive, which is why the 2 protons don't overlap. But at that particular distance, there is a high level of attraction. The strong force is the strongest force. However, it acts only over an extremely short range and has no effect outside the nucleus. How does this force create an interaction between the quarks? It's thought that exchange particles called gluons are responsible for the strong force. They act between the quarks in a neutron and a proton. Let's hear a little bit more about this.
Welcome to our series on the 4 fundamental forces of physics: gravitation, electromagnetism, the strong force, and the weak force. Today, we're starting with the most powerful of them all, the strong force. The strong force is not something that you interact with on a daily basis, but it is what holds your atoms together, so that's important, and it does it in a couple of ways. It not only holds the atom's nucleus together, it also keeps the protons and the neutrons in the nucleus from busting apart. Today, we're going to focus just on this second effect, how the strong force keeps the protons and the neutrons together through what's sometimes called color force. Neutrons and protons are both a type of particle called a hadron, and hadrons are made of even smaller particles called quarks. Quarks are a fundamental constituent of matter, and if you want to know more about that, you can listen to a whole song that I wrote about it. But it's important to note that by fundamental, I mean that they cannot be broken down into other particles. They are a fundamental constituent. Quarks and their friends leptons, which include electrons, are the most basic components of matter in the universe. Now, among their many weird and cool traits, quarks have a property called color. and it's not the kind of color that you're thinking of because you can't see quarks. But colors are how physicists describe the three different quantum states that quarks can exist in. One we call red, one we call blue, and the last one is green. Quarks are assigned these colors because all hadrons are required by nature to be, as we describe it, colorless, meaning that the color components of the quarks have to cancel each other out. This would be analogous to the way that mixing red, green, and blue light makes white light. Now, protons and neutrons are each made of 3 quarks, so this rule means that protons and neutrons can only contain 1 quark of each color at any given moment. Just to keep things interesting, and also really annoying, quarks are constantly changing color, and the process that lets them do that is also what holds the quarks together. It's by exchanging some awesomely powerful particles called gluons. So each fundamental force has its own special force carrier that's exchanged between particles that are controlled by that force. The gluon is the force carrier for the strong force. It has no mass, no electric charge, but it does have color. So as gluons pass between quarks, they change the color of the quark that they leave and the one that they go to. And they do this in such a way that the colors of the quarks always cancel each other out to keep the hadron color neutral. So that's weird, but how does this bind the quarks to each other? Well, color force doesn't work like other forces, like gravity, which is stronger near a massive object and weaker as you get further away. Instead, the color force acts on quarks as though the gluon exchange were forming rubber bands between them. Quarks can move around inside the hadron, but if they stray too far away, the color force becomes very strong and yanks them back with enormous force. This is why quarks are never observed floating around by themselves, and it helps explain why 3 quark hadrons, protons in particular, are extraordinarily stable. Amazing, right? Well, I'm not done, because in fact, the strong force is so freaking strong that a residual effect of this is that it's able to hold the whole nucleus together. That's called the nuclear force, and that's what we're going to cover next time.
Okay, so you don't need to know any of that for the IB, but I wanted to give you an insight into just how complex it really is. So we can just visualize this gluon particle as a connecting force and just leave it at that. The weak force is another nuclear force. It acts over a very short distance and is not a force that we are aware of outside in real life, shall we say. It's associated with a change of quark structure or quark flavor. The only practical example of when you should be familiar with this is in nuclear physics with the emission of the beta particle. When a beta particle is emitted, a neutron turns into a proton, or a proton turns into a neutron. And now you should understand how that's actually a change in the quark structure. In the case of a beta negative particle, a down quark becomes an up quark, releasing a W boson. In this case, it would be a W minus boson. A positron is released when an up quark becomes a down quark. In that case, a W plus boson is released. These then have interactions which become lepton interactions. But we'll talk a little bit more about this kind of changing of a boson into a fermion later. The photon you have come across before, and it is the equivalent of a light or electromagnetic radiation particle. And so it describes a discrete amount of that electromagnetic radiation. The graviton is the particle that's associated with the force of gravity, and this hasn't been discovered yet. Interestingly enough, gravity waves have been measured, and as a phenomena they do exist. So maybe it's a matter of time before we find the gravitational force carrier. So those are the 4 bosons, and here's a bit of a summary.
It's a Subaru. I'm so attracted to you. You mean because of one of the 4 fundamental forces of physics, namely gravity?
Yeah, gravity, that's it.
Hey guys, thanks for watching D-News. It's Trace and Julian here. Theoretical physics can get super complicated, as you probably know. M theories, grand unified theory, gravity waves, quantum, everything is crazy.
Now, the standard model of physics is a little easier to wrap our collective noggins around, but even still, there are knowledge gaps. For example, this week, physicists published in Physical Review Letters that they discovered a particle that might hold the universe together.
Oh. Great, no big deal then. That's cool.
Yeah. But the particle, which has a name, but I have no idea how to say it, is comprised of two quarks. Together, these tiny particles are 3 times heavier than a proton and might give hints as to how an atom's nucleus holds together.
We know the strong nuclear force holds the nucleus together, but how it works is a mystery, in spite of it being one of the 4 fundamental forces of physics.
Now, the 4 fundamental forces from strongest to weakest are the strong nuclear, the weak nuclear, electromagnetism, and gravity.
You already know what strong nuclear does. It holds atoms together, overcoming the repulsion of positively charged protons from each other. Weak nuclear is what causes the beta decay of atoms. Weak nuclear allows for the buildup of radioactive isotopes and thus the creation of something like deuterium that helps the sun burn.
Subatomic forces are very difficult to study because of the scale of the objects. So the announcement of the particle d whatever is a big deal for physicists.
Though admittedly, it doesn't really do much for you day to day.
Unlike the other 2 fundamental forces which are acting on you right now. The most obvious is gravity, which holds you to the planet to the sun to the galaxy together, and so on and so forth. But we'll come back to that in a minute.
Electromagnetic force is what causes static electricity to hold, say, a balloon on the wall after you rub it on your head.
Or the force that makes magnets attracted or repel each other.
Both gravity and electromagnetism are properties of matter. They're directly proportional to mass and electrical charge, respectively, and they both have infinite range. The gravity of the moon is acting on you right now.
Now, the mind blower is that of all of these, gravity is the weakest. Seriously, a balloon or a rocket can overcome gravity. The Earth is unfathomably gigantic in comparison to me, and I'm defying the entirety of its gravity right now. Though, not for long.
Physicists found a particle on the quantum level that aligns to each of these 4 fundamental forces, mostly. The strong nuclear uses pions and gluons. The weak nuclear uses W and Z bosons.
Electromagnetic force uses photons, yes, the same as light energy, because light is part of the electromagnetic spectrum. Gravity uses gravitons, which is tricksy.
Albert Einstein said gravity works because it curves the space-time continuum around all objects. The larger the object, the more gravity, but why is a mystery. Scientists have never found a graviton, though they have discovered gravity waves, maybe. The jury is still out.
Gravity is so confusing because we can't explain black holes with current gravity calculations, and it seems to break down at the atomic level, too.
In the end, the 4 fundamental forces of physics might sound decided and explored, fundamental forces, but scientists are still scratching heads a lot.
Now, do you want to know more on